TK, everybody. TK, 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 TK to YouTube. Okay. All right, guys. Well, hey, we're here. Second to last lab. And this is probably one of the more jam-packed labs I think that we've had all semester. And to be honest, I think this is probably the most jam-packed lab we had. You know, maybe a lot of you would think that the muscle labs were the ones that were the most jam-packed, but I think this just takes it to that next level, okay? We went through a lot of different things in this lab. Taste, smell, hearing, equilibrium, eye, and vision, okay? All the special senses. And furthermore, we had to talk about the irrelevant anatomy associated with all those senses. There's a lot of stuff, okay? And as you can see here from the learning objectives, there's 14 different learning objectives we expected you to know at this lab. So because of that, I think this is the lab that I think just took it to that next level, okay? But what we're going to do, at least for the video, is the way I think we're going to do this is get taste and smell out of the way, and then also talk about the associated experiments as we go through them, because there's just too much stuff that comes with hearing and equilibrium and eye with the anatomy. I just want to take as much time as we can to focus on that stuff in their respective videos, and we can crank through these experiments really quick because they're really, really fast, really simple. Okay. So 14 learning objectives. I'm not even going to go through them. There's so many things here. Just pay attention to what they're asking, of course, and what they want you to know. A lot of this stuff is pretty self-explanatory, what it wants you to know. So, like, name the 5 primary taste sensations. Like, we do that right away in the pre-lab prep. Describe the location of the olfactory receptors. If you watch my video from last week on the cranial nerves, you'll find it there. I'll show it here in the video again. And then, honestly, what I might do is just circle back around to the learning objectives for the ear and the eye as we get to those sections, respectively. So, like I said, we'll crank through taste and smell, talk about all the experiments throughout this entire lab right away, and then we'll just keep cranking through there, okay? So, 14 learning objectives. Make sure we know these guys, have them all hammered down. Let's give it a whirl, though. Let's get into this thing. So, pre-lab prep, what we had to do. So, taste. 5 different taste sensations that we have, okay? Well, that comes with every single food. And they're all distinguished based on just kind of different, flavors that or different taste, I don't know what you want to call it, taste flavors that we have, okay? And this is what they are respectively, okay? So, sour is the first one. Sweet, all right. Salty. Everyone loves salty, I feel like. You get the saltiness from bacon or French fries, which I love. Okay. Bitterness. And then the last one was kind of a weird one, if you remember. It was called umami. Okay. Bit of a weird one there. Okay. But what are these guys associated with? Okay. Let's talk about that. So what is sour associated with? So this would be like acids. So like citrus fruits, for example. Okay. Sweetness. What this guy is associated with is primarily going to be like the sugar from fruits. So sugar would be primarily like from like bananas, for example, because bananas, as you know, the longer they sit out, the longer you don't eat them, they turn that brown color. That's extra sugar. The bananas are essentially secreting. So that's where the sugar comes from. So salty, this comes from the metal ions in food. So metal ions would be like K plus, for example. So we'll do K plus. That would be potassium, and then you could also say Na plus too. That would be sodium. Okay. Bitterness. Let's see here. There we go. Bitter. So bitterness, where this comes from, this is probably going to be like caffeine or nicotine, for example. That's where the bitterness taste comes from. Okay. Nicotine, I think that's how you spell it. I don't consume nicotine or caffeine for that matter, so I don't really know what bitterness is primarily. And then umami is, this is kind of a weird one because one, it has a weird name, okay? And then 2 is a distinguishing one amongst the amino acids, okay? So primarily you get this one that comes from like different types of meat, so like steaks or hamburgers, chicken, for example. That's where you get this from, because amino acids, if you guys ever have to take a nutrition class, they are the building blocks of all proteins. So proteins, when they're broken down, they're broken into respective amino acids. That's where that taste usually comes from. Okay. So taste, really, really simple. Okay. So 5 different taste sensations. List some examples of foods and substances. So there's just some examples right there. Define sensory adaptation. So this is associated with smell. Okay. Smell, I think, is one of the most unique senses that we have. it plays a heavy role when it comes to taste, as we will talk about one of the experiments. So smell and taste are really, really interrelated. But smell also has a really, really high, what's the word I'm looking for? High connection to our emotional centers in the brain. So if you've ever, walked by or smelled something and it, maybe it smells really, really good, okay, or has a certain smell to it. And depending on how that smell is, it actually can trigger the emotional centers in our brain to remind us of past experiences we've had, okay? So really weird example, okay? So sometimes I get, dryer sheets, and some of them, sometimes have smells to them, right? So there's one particular brand of dryer sheets. I think it's like I think it's like a downy, like lavender or something like that. I forget what it is. Every once in a while I'll get it. When I get it and I smell it, it brings me back to a time when I was in undergrad, because I remember from a certain period of time those were the only dryer sheets I was buying. So it's really unique. So smells can play into past experiences and past emotions you've experienced. So when I smell that dryer sheet, it brings me back to a time when I was in undergrad. I think it was my senior year of undergrad, which was during 2020. Senior year of undergrad was during 2020, the fall, when it was just me living at my apartment all alone, because my roommates didn't come back. They stayed at home and did their stuff online. So it was just me living by myself in my apartment. I don't know. It's really, really unique how smell can play into that. And maybe you guys have had some experiences in the past, or maybe going forward now, you'll think about that, okay? Anyways, getting off that tangent, what is sensory adaptation? Okay, so sensory adaptation. So with prolonged stimulation, okay, the firing rate of neurons will decrease. All right. Thus, we don't. Gosh, spelling once again, guys. I told you about that all semester. So then we don't notice the stimulus as time goes on, right? And we probably notice this, right? Maybe you light a candle or something like that, right? You light a candle, you notice that smell right away, and then as time goes on, you start to, not notice that smell as much, okay? And that's because our olfactory receptors go under this sensation, this thing called sensory adaptation, which as the stimulation of the smell goes on, our olfactory receptors start to turn off because we don't need to notice that smell anymore, okay? So our olfactory receptors, are they phasic or tonic, okay? So what this is referring to, okay? So first of all, let's talk about the both of them. So phasic, okay? So what is this? This means that they respond quickly, okay? Which means, but only for a short time, okay? What that means is that as something gets stimulated, okay, what's going to happen is that they're going to start responding really, really quickly, all right? Which means we won't notice them, okay, in a short amount of time. So once again, example, candle, you smell it for 10, 15 seconds. As that time period goes on, you continue to smell it. You're going to not notice that smell, okay? So it's going to go really, really, really quick, all right? Versus on the other hand, we also have tonic, all right? So you respond slowly, but continues action potentials, all right? So what would be examples of this? So this would be like pain cells, right? We want to be able to be able to understand when we're in pain, right? We don't want to be able to adapt to that quickly, because pain is our body's way of telling us that something's wrong, okay? So if we're having pain, that's our body's way of telling us something's wrong, okay? If we respond to that or adapt to it too quickly, that's obviously not a good thing, right? We want to be able to know when we're in pain so we can treat it accordingly. So we want to know when we're having pain. So pain cells do this. Touch receptors also are like this too, so they take longer. So whenever you put on pants or jeans or whatever, it takes a little bit longer for our body to, get used to us wearing them, right? It takes some more time compared to the phasic receptors. The one that's most important here, I think, is pain, right? We want to be able to understand when we're in pain, and we don't want that sensation to go away very quickly. Obviously, you don't want to be in pain, but we need to know, our bodies to know when we're in pain, okay? So which ones are our nose then, okay? So as our olfactory receptors, are they phasic or tonic, okay? They are actually phasic, believe it or not. So let's highlight that. They are phasic. And the way I remember phasic being fast, okay, is pH. And I spell that fast with a pH in it, okay? So so instead of with an A, or instead of with an F, fast, just like that. Okay, that's how you know. All right, olfactory receptors are phasic. They're fast because they respond quickly. Okay, that's the olfactory receptors. All right. Okay. Hearing in equilibrium. Okay, so a couple different structures here. Okay, and remember these are all related to the vestibulocochlear cranial nerve. All right, cochlea and the vestibule, along with the semicircular ducts. All right. Semicircular ducts and the vestibule are intertwined because these are related to equilibrium versus the cochlea is related to hearing, okay? So really, really easy here. Hearing is going to be A. All right, we got that one out of the way. Boom, easy, okay? Linear acceleration, then we have angular acceleration, then we have static equilibrium, okay? So linear acceleration is talking about moving, all right, in a forward to backward, right? So like up and down, like in an elevator, and walking in a forward direction, okay? So that's linear acceleration, okay? So up and down. Angular acceleration is with rotations, right? So if we're shaking our head or something like that, or maybe we're on like a tilt-a-whirl or something like that, the angular rotation and stuff, okay? So how our body is associating things in the Z direction, okay? The Z direction, X, Y, and Z directions. The Z direction is more that rotation one, okay? So semicircular ducts, that's going to be that one. And then the static equilibrium, so then if we're just sitting here, if we're just lying down, this allows our body to not be able to get dizzy and allows us to know where we are in space. This one is also going to be the vestibule down here. Okay? Very, very easy. Okay. Eye muscles. Remember, we talked about these guys this past week. All right? We talked about the innervations, the 3 different cranial nerves here, okay? Remember, 3 of them, okay, 4 of the muscles, excuse me, are innervated by the big bad cranial nerve number 3, oculomotor, okay? Which one is that going to be? That's going to be the medial rectus here, okay? So we'll do that. That'll also be this one here. Also going to be inferior rectus. Not superior oblique, but it's also going to be the inferior oblique, okay? Lateral rectus, remember LA. Remember that abbreviation, LA? Lateral rectus abducens. Lateral rectus abducens, LA, okay? Abducens is number 6, all right? Superior oblique, this is number 4, trochlear, okay? ST, STO, SOT, SOT, STO, whatever jumps your boat right there, okay? So this is number 4, trochlear, okay? And that's it for the, that's it for these guys, okay? So that's it for pre-lab prep, taste, smell. So now let's move down here, okay? Let's start talking about some of the stuff that we got into lab with, okay? So remember, the tongue is primarily organized or primarily involved with taste. It's covered in papillae. If you stick your tongue out, you see, look in the mirror, you see those small little projections or various shapes and sizes. Those are called papillae, all right? Some papillae are designed to sense the texture of food, and most contain taste buds and taste cells that are in them, okay? So I think if we look over here at our anatomy model, we should be able to find the tongue, and we should be able to see the papillae over here. You guys can visualize this stuff. So let's look at the tongue here. And this would be that, a very, very blown up image of what the papillae look like, okay? So you have, different, you have the filiform papillae here, you have the circumvallate papillae. I didn't have to learn these guys in super big depth in school or anything like that. I just had to know what they were and just, what the general function of all the collective papillae were. And that's for taste buds, taste cells, and this, interpreting the texture of them, okay? This is a very blown up image of it. And this is obviously what the tongue would normally look like, okay? Normally would look like. And we don't need to know the different regions of the tongue. We just got to know what the taste buds are, okay? So 5 primary sensations. Once again, okay, what are these guys? We have sour, sweet, we have salty, we have the 3 S's, right? And then we have bitter, and then we have umami, okay? So 3 S's, sour, sweet, salty, bitter, umami, all right? Easy peasy. So what were the experiments we had to do for this one, okay? So what we had to do is how the impact of smell and the taste and taste perception are associated, right? We talked about that. How smell and taste are really, really highly associated. So what we usually do for determining how something tastes is we analyze its texture, we analyze the smell, we analyze the temperature of it, and we analyze the appearance, okay, how it looks. So what this experiment was, okay, what we wanted you to do is we wanted you to use particularly some Lifesavers candies, okay? And everyone could have done this, one person could have done this, whatever you guys wanted to do, okay? What you're supposed to do is get the Lifesavers candy, and you didn't want to let the subject know, what color, what flavor they were being given, anything like that. You wanted to completely blind them to that, okay? So the subject was supposed to close their eyes and hold their nose, so plug your nose, okay? Give them the Lifesavers candy, okay? And then while they were still holding their nose, they were supposed to try and guess the flavor of that candy, okay? So try and guess it with your nose closed. Then you release your nose, so you take your fingers off your nose, you unplug your nose, then guess the flavor, okay? What should have happened, okay, is that the flavor should have been more easily guessed when you unplugged your nose, okay? And we wanted you to try and see if you can guess it with your nose plugged and when your nose is unplugged, okay? When your nose is unplugged, it should have been easier because now you're using smell to associate with what the flavor is, okay? That's what I was saying. The smell and taste are highly associated with each other, okay? So if smell is missing, most of the time you aren't going to be able to understand what the taste is, okay? How something is tasting, okay? So smell is one of the most powerful factors involved in taste. Lists 3 other factors that can influence the perception of taste. This is going up here to these guys. So texture, temperature, and appearance, once again, okay? Super easy experiment. And hopefully you guys got a little bit of a good, good flavored candy out of it too, okay? All right. Smell. Another really easy one here, okay? So smell differs from taste in terms of range, okay? Taste requires actual physical contact between a substance, as we know. Smell can operate across a variety of differences, right? We know that. Candles, right? They're situated on the opposite side of the room. We can smell them. I remember back when I was in high school, every single day, I would drive by this water treatment facility in Sun Prairie, Wisconsin. And of course, it had sewage water going through there. And the smell, I'm a mile, quarter mile away from it, you could just smell it, right? It's something you can easily smell. So, great example there, how it can travel across long distances, right? The olfactory receptors are found in the patch of epithelium called the olfactory mucosa, And this is at the roof of the nose, okay? And remember, we talked about this. I showed you guys in that in the video last week, okay? We talked about it with the cranial nerves. So remember, olfactory nerve here, as we kind of look underneath, we can see those little fibers that are under there. Those are those olfactory fibers that are puncturing through that cribriform plate. And if we look into the most upper roof part of the nasal cavity, we can see those guys once again, okay? The guys highlighted in blue. So way at the top part of the nasal cavity are where the olfactory receptors are, okay? So what this experiment was trying to do, okay? What it was trying to do. You were trying to determine which part of your nasal cavity is most sensitive to odor, okay? So what we gave you was a timer. We gave you a little plastic inhaler, which is like a little plastic tube, and 1 vial each of oil cloves and an oil of peppermint from the bench, okay? So choose either of those two. You open the lid up and you put that plastic inhaler, okay, right over the opening, okay? And the other end of the inhaler in the nostril so it points at the lower part, okay? And then you wanted to close your other nostril with it. So you wanted to have it pointing to one of your nostrils, close the other one. Inhale slowly, attempt to smell the odor. Perfect. Take the vial away, wait 1 minute. And then, after that, we wanted you to directly point it upwards to the top part of your nose. So basically parallel to the way that your nasal cavity runs, okay? So, in which position could you smell the odor better? It should have been when it was pointed directly upwards because we're allowing those particles, the olfactory particles of that smell, to go upwards, up towards the roof of your mouth. Versus when they're down here, roof of the nose is here. Roof of the nose, excuse me. Versus those olfactory particles are just situating themselves right here, okay? So when they're able to rise and go directly up towards the roof of your nose, you should be able to smell it better versus when they're just sitting at the bottom part of your nose. But, obviously when you're taking in scents, the particles should travel upwards regardless, okay? So does this make sense considering the location of olfactory mucosa? And it should be yes, because as things are pointed upwards, they're pointed directly to where the olfactory mucosa, where those fibers are. It should make it easier for you to smell things, okay? All right. Olfactory fatigue, okay? So sensory adaptation, once again, if a stimulus persists, the firing rate of the neurons gets slower over time, making you less aware of the stimulus, okay? Remember, we talked about the 2 different types, the phasic ones, all right? They generate a burst of action potentials initially. They quickly adapt and sharply reduce or stop signaling even if the stimulus continues as time goes on. Versus tonic, they adapt more slowly and generate nerve signals more steadily, okay? All right. So now what we wanted you to do, okay? So close one nostril. With the other nostril, smell the oil of cloves by holding the vial about a half-inch away from the nose, okay? Exhale through the mouth, inhale through the nose. Make sure you keep one nostril closed. Record the time it takes until the smell of cloves starts to fade. Is only faintly detected, okay? And then when you can no longer smell the oil of cloves very well, attempt to smell the oil of peppermint, okay? Are the olfactory receptors phasic or tonic? Remember, pH, AST, fast. All right, that's how you know which one's which. Olfactory is always phasic. It is fast, okay? pH, AST, fast, all right? Could you smell the peppermint after the olfactory receptors for cloves or fatigue? Display why this is important physiologically, okay? So, what you should have noticed here, okay, so after you fatigue the olfactory receptors, okay, it should have been a little bit harder for you to detect that smell, okay, because you were just smelling the same thing over and over and over again, so they're fatigued, okay? So, when you put a new smell under there, okay, either what should have happened, okay, is that it would have been a little bit harder for you to get that smell because your olfactory mucosa receptors were fatigued, okay? Or maybe, you took a little bit too much time between getting the peppermint oils into your nose, so your olfactory receptors were able to smell the natural air again. They weren't as fatigued, so then you were able to smell the peppermint right away, okay? On paper, perfect world, what should have happened is you shouldn't have smelled anything because your olfactory receptors were fatigued. That's perfect world, okay? That's okay. That's okay, though, all right? It's an experiment. So, that's the olfactory ones. Ear, we're going to go over that in a little bit. I just want to talk about the experiment we did here, okay? So, experiments we did for the ear, okay? We were looking to see if you had conductive hearing loss, okay? So, conductive hearing loss occurs when sound conduction through the outer or middle ear is impaired. Common causes is a buildup of earwax, ear infection, very common in children, and a perforated tympanic membrane or a punctured eardrum, okay? We had 2 tests that we wanted you to do. We had something called the Rene test, okay? We also had something called the Chandler-Bing test. I'm a Friends fan, so I call it the Chandler-Bing test, okay? Rene test, easy. Take a tuning fork from the front bench. You strike it on your shoe. You place that tuning fork on the mastoid process, okay? Remember, that's where your SCM muscle inserts onto, okay? That little bony prominence just behind the ear, okay? So you have the prongs facing downward as such after you strike it to the ear. Once your partner indicates that they can no longer hear the ringing when it's attached to your ear, your mastoid process, you're going to take it away. You're going to move the prongs of the still tuning fork about a half-inch lateral to the external auditory canal, so your ear hole. And that tuning fork should not be touching your lab partner, okay? So, if the sound is heard after the tuning fork is placed near the outside of the ear, as indicated right here, okay? So if you're still hearing the sound, that means it's a normal Rene test, so you don't have conductive hearing loss, okay? Versus if you didn't hear it, okay, that's an abnormal one, which means you had a positive test, which means there's something going on there, okay? So repeat that process, indicate for which ear, if you had it, you go from there. Bing test, okay? Another very, very similar one, okay? Strike the tuning fork, once again, place on the mastoid process, all right, as you did with the Rene test. But now what we're going to have you do is have the test subject, so have whoever was doing the test, okay, is you're going to close off the ear canal by placing the pad of your finger over it. So you're basically just covering your ear hole. You're blocking the sound, okay? The person with normal hearing should hear the sound better when the ear canal is closed as you have that tuning fork pressed against your mastoid process, okay? That's a normal Bing test, all right? Versus if a person with conductive hearing loss will no longer notice the sound change, so if it feels like it's the exact same, that means it's an abnormal Bing test. So it's a positive test there, okay? So the reason is that whatever is causing the conductive hearing loss, earwax, for example, is preventing the vibration of air in the outer or middle ear. Thus, only sound is heard due to the vibration of the inner ear itself, okay? So because of that, the person will hear it no differently when the outer ear is occluded, all right? So results respectively there. Eye tests, scroll down here. We'll talk about the cow eye tune a little bit. Labeling. Okay, test. Experiment number 5 here. So blind spot detection here, okay? So what we had to do here, okay, we talked about the optic disc here, and that the optic disc contains no photoreceptor cells. So it produces a blind spot in the visual field of each eye, okay? You can detect your blind spot and observe an interesting visual phenomena with the help of this figure here, okay? So close or cover your right eye, okay, and hold this page about 12 inches from your face, okay, roughly 12 inches. You want to fixate on the X with your left eye, and it should be in line with the middle of your nose, okay? So the X should be in line with the middle of your nose. So try and line it up as best you can. Without taking your gaze off the X, okay, so really focusing on it, move the page slightly forward and back until the red dot disappears, okay? What you should notice is something should happen at the same time that dot disappears, okay? A phenomenon called visual filling, okay? Where the green bar seems to fill the space where that red dot should be. This occurs because the brain uses the image surrounding the blind spot, okay, to fill in the area with similar but imaginary information. The brain acts as if it is better to assume that the unseen area probably looks like its surroundings. So the brain acts as if it is better to assume that the unseen area, so when you can't see the red anymore, it looks like the surroundings being the green line. So it fills in that red dot with the green line. It's what should have happened, okay? So why does the red dot disappear? That's because of the blind spot, okay? We don't have any photoreceptor cells there, so we're basically in the blind spot. That's why we can't see it. What is unique about the retina at the location of the blind spot, okay? What's unique about the retina is that is the area where it contains no photoreceptor cells, okay? So in that area, if you have no photoreceptor cells, you can't see anything there, okay? That's what's going on. So your brain is filling in the gaps, right? So your eye isn't doing the work, right? Your eye is not filling that in. Your brain is making it up for you. It's imaginary information, as it says here, okay? That's what's really unique about it, okay? The accommodation, the last experiment, okay? We're almost way over time, okay? We're almost at 30 minutes. Let's go through this. Accommodation is the change in curvature of the lens to focus on nearby objects. When focused on an object at a distance more than 20 feet away, the light rays coming from that object are essentially parallel, and thus can be focused on the retina without much effort. In this case, the ciliary muscles, okay, surrounding the lens are relaxed, which tightens the ligaments and makes the lens flatter and thinner. When you look at something nearby, the ciliary muscle surrounding the lens contracts, okay? So when you're looking at something up close, the muscles contract, the ciliary muscles contract. It relaxes the ligaments holding the lens and allows the lens to become more thicker and more convex. A more convex lens refracts the light more strongly, thus focusing the divergent light rays onto the retina, as seen in figure 12.15 here, okay? So, distant vision. What's going on here? Relaxed muscles, tighter ligaments, the lens is more thin, okay? Versus when you're looking at something up close, the muscles contract, ligaments relax, lens thickens, okay? That's for near vision, right? So, near point of vision test. The closest an object can be and still come into focus is called your near point of vision. The near point of vision depends on the flexibility of your lens, which stiffens with aging, and it's why we need to have readers as we get older. It's an unfortunate part of aging. To determine your lab partner's near point of vision, have them hold this page out in front of their arms in front of you at arm's length. Instruct them to close one eye, focus on the words "Anatomy is fun" written below. Okay. Now have your partner move the page toward their face, okay, and determine the minimum distance from their face that the words remain in focus. The minimum distance is basically right when the words start to become blurry, okay? That's the minimum distance. Use a ruler to measure the distance in centimeters and record below. Repeat this process for the other eye, okay? So, do it you can see basically what your near point of vision is, okay? So as you get older, all right, what's going to happen is you're gonna lose that sense of your near point of vision, okay, unfortunately. And it's just, like I said, it's an unfortunate part of aging, but it's something that just happens, okay? Unfortunate part that happens with aging. Okay, that's all the experiments there, guys. Okay, so I wanted to go through all the experiments first, so that way you can talk about the relevant anatomy, specifically with the ear, because this thing is jam-packed, okay? And we'll talk about the eye, and then we will also talk about the cow eye dissection too, okay? So, ear on deck, buckle your seatbelts, got a lot of stuff we got to talk about. We'll go from there. All right, guys, I'll be back in a little bit.